right, the last thing that I want to look at is this idea of z mod pz, and p is a prime. And we've been using this language for quite a while, and in mathematics we typically don't always refer to it as z mod pz. Sometimes we do, sometimes we don't. It's more common to see this sort of notation, f p. And what this means is that it's a field f with p elements. All right, and in this case, I'll also say that this subscript means that it's a finite field. Okay, finite, not infinite, or it's just an element or a field containing p minus 1 things. Right, you would go from 0 up to p minus 1. Okay, so that's some notation you might see. We can talk about finite fields, we can talk about fields in general, but every finite field has to have all the property of fields. And so here you can see I've defined what a field is. In mathematics, we have to have a field. We talk about having two operations. Typically, when we're working with real numbers, we can work with other things. But when we're working with real numbers, it has to have two operations. Again, any field has to have two operations. Just when we're working with numbers, we define them to be addition and multiplication. And so then we have to have associativity. And so just as a reminder, associativity is like you have A, B, and C, and you have A, B, and C. And really all associativity is saying is that you have the difference in chunking. So you can have plus here, plus and plus and plus, or you can have multiplication. Okay, it doesn't matter how you chunk them, it's the same. That's this idea of associativity. And commutativity means that if you have elements like A and B, this is typically equal to B and A, and so you can either add those or multiply those in either order. Okay. Also within a field, there's multiplicative inverses and identities, as well as additive inverses and identities. So you have something like A times A inverse is equal to the multiplicative identity 1, and actually this is the same if you do it in the other order. Okay, it has to be true in either order, and so that's a multiplicative, and additive would just be if you have A plus the opposite of A, however that is defined in the field, that has to be the the additive identity of 0, and conversely, if you do it the other way around, same thing. Okay, and then lastly, distributivity of multiplication over addition. So this is the idea that if you have A, B, and C added together, you can, and multiplied there, you can write this as AB plus AC multiplied together in there, and then it's actually the same thing if you do, so that would be called left distributivity. You could have right distributivity as well. Same thing, and then with commutativity, it doesn't matter. Okay, so field has to have those four things. There's a lot embedded in there, and so what I would encourage you to do is show that F4 is a field. And so here, notice that the 4 is not a prime number, certainly, and it's just saying that it's a finite field with 4 elements that are 0, 1, 2, and 3. And so I want you to pause the video and think about how you would show all 4 of these properties for F4. Okay, now there's a lot of different ways you can show this. Perhaps the easiest way to show this is through creation of tables, kind of like what we did with the z mod 7z in the previous video. So you could make tables like a table for addition of 0, 1, 2, and 3, 0, 1, 2, and 3. And I'm just going to put these dots in here. And then same thing for multiplication. 0, 1, 2, 3, 0, 1, 2, 3. Okay, and so complete these tables quickly and then resume the video when you're ready. Alright, and so I forgot to mention that this field is actually mod 4. Okay, I think you may have picked that up. But in looking at this field, so I completed the two tables for addition and multiplication. So under addition, I certainly have the additive identity. I have an additive inverse. Actually, do I? So how would I see the additive inverse? What would be the opposite of A? So it would be what I would need to add to 0. So for example, 2 is its own additive inverse, because if I add 2 twice and I get back to that additive identity. 3 and 1 are additive inverses because, again, if you add them, you get to the additive identity of 0. Okay. Associativity and commutativity, you could show that in here if you wanted to. I think the table does a pretty good job of showing that. For example, if you do like 2 over here, the 2 on the left, and then 1, you get 3. But then if you do 1 and 2, you get 3, so that shows commutativity at least. For associativity, you might have to do a sequence of 3 things. I'll let you figure that out. And then distributivity is, we haven't talked about distributivity yet. Let's look over at the multiplication table. So multiplication table, 0 is not too surprising. 1 is the multiplicative identity because if you multiply it by any other element, you get that element. And then in terms of multiplicative inverse, it is commutative. So for example, if you do 2 times 1, you get the same as 1 times 2. Okay, that's fine. And then let's see, we're kind of going through and just verifying these verbally. You'd actually need to like write all this down. For multiplicative inverse and identity, I talked about multiplicative identity being 1, multiplicative inverse, certainly, so 3, if I do, let's see, 3 times 3, that's its own multiplicative inverse, as is 1. But then I actually encounter a problem, right? If I look at 2, and I'm just going to highlight these two, if I look at 2 in either row or column, I don't have 2 times anything equaling the multiplicative inverse, okay? So sometimes mathematicians use this as a field of 4 elements, but actually, when they do that, they're not referring to these typically because this is not a field. It violates the multiplicative inverse property. Okay, so no multiplicative inverse for 2. Okay, but so this is a nice counterexample of something that is not a field, and so even though it says verify, I could, surprise you. Some things that are fields, something that we work with all the time, the real numbers. Okay, and then by extension, the complex numbers, but we're not going to really deal with those. And then certainly the rational numbers are fields as well. Something that is also not a field, integers. Okay, how do you talk about multiplicative inverses within the integers? And then by extension, the natural numbers. Okay, both of those are not fields. Okay, so we'll get some more practice both verifying field properties and working with fields in class and in later lessons.